Okay, good morning everyone. Today we are going to start looking in Chapter 9. Chapter 9 is all about significance tests, and in particular we're looking at significance tests for proportions. And this section is about the basics of what significance tests are all about. So if you want, you can pause the video right here and take a look at these objectives that we'll be covering in this section. In Chapter 8, we estimated the value of a proportion, of a population proportion, by calculating confidence intervals. So we took a sample, we used that sample to calculate a confidence interval. Okay, in this chapter we will test the validity of a claim about a proportion, and we express our results as a probability. This test is called a hypothesis test. Okay? Hypothesis testing. So here's an example. I'm going to let you pause and read this in detail, but what we're talking about here is a plant where we're making something called an ingot. I think that's how you pronounce that. And some of them come out with cracks and have to be redone. So we have a new process, we've made some improvements, and we now take a random sample, and it should say that there's 400 here. It doesn't say that, so it should say that. So we're just going to write that in here. 400 new items, new parts were processed, and 17% were found to have cracks. So the question is, can we say the new process is better? It's a yes or no question. So we're always going to answer yes or no. All right. We see questions like this all the time when we make changes to things. We want to know whether or not the change that we made has made any difference, or just in general. For example, have teens stopped smoking or smoking less this month than last month? We put an ad in the Super Bowl. Did that actually make a difference? Did it increase our sales? Is the global temperature increasing? And so on. So to answer these questions, we test hypotheses. We will start with the null hypothesis. The null hypothesis always assumes no change. Okay? So we start in our example with the ingots. We start with the assumption that the new process makes no difference. In other words, the new proportion of cracked pieces is going to be 0.2, same as the old. Notice the notation here, H with a little sub O or 0, colon, P, the proportion of the population, is still equal to 0.2. The alternative is that there has been a change, okay? There has been a change. The new method will decrease, in this case decrease, not always, the proportion of cracking. Okay, so here we have HA, the alternative, A for alternative, P is less than 0.2. Question, how much smaller would the sample cracking rate have to be in order to convince us that the new method is better? Is 0.17 low enough, or is it not low enough? Whoops, I went the wrong way. Okay, so in this case, although our sample was not drawn at random, the engineers believe that we do have an independent process. So we can go ahead and use our normal model for this. Also, because our expected number of successes, which is 20% of 400, and failures, 80% of 400, are both more than 10. Notice here we're using the 20%, the 0.2, which is the hypothesized value. We always want to use that value when we calculate our NP. This is NP and N1 minus P. All right, so using our normal model, we have this formula for the standard deviation. And in this case, we're going to use the 0.2 that we know. So we're going to put 0.2, 1 minus 0.2 over 400 is 0.02. So this is the standard deviation. What does this look like in a normal model? We'll pull this model up so you can see it. So we have a mean. The mean is I don't know if I can write on here. Yes, the mean is 0.2, which is our hypothesized proportion. The standard deviation is 0.02. So 0.2 minus 0.02 is 0.18, and so on and so on. Our sample was 0.17 right here, right? So we can see just by looking at this model that there's a pretty good chance, you know, this is not tiny area, that our sample was from a population whose mean was 0.2. All right. In other words, the conclusion that we would make here, and we're not going to do it in detail right now, is that 0.17 is not unusual enough for us to conclude that the new process has made a difference. And we're going to do that more formally in some other examples. All right, here's another example. Suppose that New Jersey's motor vehicle department says 80% of candidates who come take a driving test pass on the first try. How many of you passed on your first try? The Bergen Record, our newspaper, does a random sample of 90 local teens and finds that 63 have passed. So 63 out of 90 is 63 divided by 90 is 70%. So does this, so this is our p hat, right? This is our sample p hat equals 0.7. Is that enough to convince us that the actual rate for teens is less than 0.8? Okay, so our null hypothesis, let's go to the next screen. Well, I'll come back to this in a second. So the null hypothesis, p equals 0.8, and our alternative, p is less than 0.8. Okay, notice that our sample does not show up in here right now. Okay, so the claim we weigh evidence against in the statistical test is called the null hypothesis. The claim about the population we're trying to find evidence for is the alternative. So we start by assuming the null is true, and we're looking for evidence to say that it's not true. Okay. All right, what would convince us that the proportion of drivers who pass on their first try is less than 80%? How much smaller must the sample proportion be so that we would be convinced? This is the crucial question in a hypothesis test. And in general, this is how we write our hypotheses. Null hypothesis always equal. Okay. Alternatives can have one of these three forms: less than, greater than, not equal to. The hypothesis should express the hopes or suspicions that we have before we see the data. It is cheating to look at data and then make hypotheses. Notice hypotheses always refer to a population and population parameters, never sample. These are samples, okay? Now, in this example, we've seen this before. We have our basketball player making 80% of his free throws, he claims, but actually he makes 32 out of 50. I should say out of 50. What can we conclude about the claim based on the sample data? So we did a simulation. Here's what we got, okay? We found that only 3 out of 400 times is the probability, is the sample. This is 64% or less. So that's pretty low. So that would lead us to believe that our basketball player's claim is false or is not true. Okay, the reasoning of significance tests, there are two possible explanations for the fact that he only made 64% of his free throws. One is that he actually is an 80% free throw shooter, but this just was a very unlucky outcome. The other is that he's actually not an 80% free throw shooter. So the null is correct, the alternative is correct. There's two possible scenarios. One of these is true, the other one is not true, okay? The idea here is, but let me go back for a second. One of these is true, the other one is not true, but we don't know which is true and which is false. Okay, so we're going to use our sample to come to a conclusion. Of course, in statistics, we're never 100% sure. But the outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. And so we say in favor of the alternative. We reject the null hypothesis in favor of the alternative. Okay, so when we do these tests, there's three scenarios. Remember I said we could have greater than, less than, not equals to. These two are called one-sided. Okay, one-sided tails because we only have area on one side and not the other. And then sometimes, rarely, but sometimes you want to test whether or not the new proportion is not the same as the original or hypothesized proportion. So that's a not equals 2. So that's a two-sided test. Okay, and the question we ask are these data surprising given that the null hypothesis is true? What is the probability of seeing data like this given that the null hypothesis is true? This probability that we will calculate using our normal processes is called the p-value. Not to be confused with p, which is our proportion, population proportion. So the probability is called the p-value. And how do we interpret p-values? The probability that the sample statistic could occur given that the population parameter is as stated in HO. So in other words, the probability that we got the sample we got given that HO is true is called the p-value. Smaller p-values are evidence against the null hypothesis. So if this probability is very low, then we say, well, maybe we're going to reject the null hypothesis. Larger p-values fail to give evidence against the null hypothesis. So notice what this says here, very important. We fail to reject. We never accept the null hypothesis. We fail to reject it. Okay, this is kind of saying the same thing. Okay, so there's two decisions you can make. You can either reject or fail to reject. If you reject the null hypothesis, then the results are statistically significant. Okay? And there is evidence that there is a difference. If you fail to reject, the results are not statistically significant, and there is not evidence of a difference. Oops, something's going slow here. Oops, here we go. Think about a criminal trial. The defendant is innocent until proven guilty. If the verdict is not guilty, however, we never say they're innocent. We just say there's not enough evidence to say that they are guilty. Similarly, we never say that HO is true. We just don't have evidence to say that it's false. Okay, so now how do we decide? How do we decide how much evidence is the right amount of evidence? Well, we've been talking about this all year long. We're going to put a formal name on it now. We've been talking about 5% being our kind of rule of thumb, if you will. So now we're going to put a name on that. We're going to call it a significance level alpha. Okay, so much of the time we set alpha equals 0.05. You don't have to, but that is the most common level for alpha. So if this calculated p-value is less than alpha, we say the data are statistically significant and we reject the null hypothesis. Okay, if we used, let's see, and we conclude there is convincing evidence in favor of the alternative. All right, so when we use the fixed level to draw a conclusion, p-value is less than alpha. So this is the probability, okay, of getting the sample we got if HO is true, is less than alpha, let's just say as example 0.05. We reject the null hypothesis. We have convincing evidence for HA. If p-value is greater than or equal to alpha, so greater than or equal to 0.05, we fail to reject. We do not have convincing evidence. All right, so let's just take a look at this one. There's a lot of repetition in here, but hopefully it's helping because this is a little bit complicated. So here's the test result. We have a sample. We calculated the p-value. If the p-value is large, we say the results could just be due to chance or sampling error, and we fail to reject. P-value is small. The results are unlikely if HO is in fact true, and therefore we reject HO. Okay, let's talk about errors. So of course you can make a mistake because we're not 100% certain. So you can have evidence against your null hypothesis and therefore reject your null hypothesis, but in fact your null hypothesis could be true, because remember, there is a truth about the population. The truth about the population doesn't change, it's fixed. So maybe that is true, but we reject it. That's called a type 1 error. Or maybe it's false, but we don't reject it. We fail to reject because we got evidence, we didn't get evidence in our sample that would cause us to reject. That is called a type 2 error. So think of this little trick when you're trying to remember which is type 1 and which is type 2. A type 2 error is where we fail to reject. Okay? Little trick.